The next example is about a pump. We know that pump increases the pressure and temperature of liquid water, right? Unlike a compressor where at the inlet usually it is steam, in a pump the inlet is liquid water. And therefore in this example, let's read the problem statement. Water enters a pump at 100 kilopascal and 30 degrees Celsius at a rate of 1.35 kilogram per second and leaves at 4 megapascal. Okay, so we have a pump. At the inlet we have 100 kilopascal of pressure and 30 degrees Celsius. The mass flow rate is 1.35. And exit, the pressure increases to 4 megapascal. If the pump has an isentropic efficiency of 70%, determine A, the actual power input, B, the Exergy destruction, the rate of Exergy destruction, and let me see, the second low efficiency. If the environment temperature is 20 degrees Celsius. Okay, of course we know for pump to increase the pressure it requires a power input, right? And in this problem we will have to calculate the actual power. But interesting thing here is they are giving us the isentropic efficiency. Okay, so we should be using that isentropic efficiency equations. So the isentropic efficiency equation for a pump or a compressor is, we have isentropic power in numerator and actual power in the denominator, because the actual power input is bigger than when it is an isentropic case. Okay, so now we know the isentropic efficiency is 0.7 or 70%, and in order to find the actual power, if we can find isentropic power, we would be able to use the find the actual power. So to calculate the work per unit mass for a steady flow reversible device, we were able to use this equation, right? It was V dP. Okay, and here remembering that at the inlet we will have water and it is a pump and it is an incompressible substance, therefore we can assume throughout the process specific volume doesn't change, so we can just say that. And this will tell us actually the work per unit mass in this process is, we can just find it from specific volume times P2 minus P1. Of course, in order to find the power, we need to multiply this with the mass flow rate. So, but first of all, let's look at the first state properties so that if we can figure out the specific volume at the first state. So we are given the temperature to be 30 degrees Celsius and the pressure to be 100 kilopascal. With this information, we figure out we have compressed liquid. It should lead us to the saturated water tables, where we read the information for properties such as specific volume. We can read entropy, enthalpy properties, right? So these are what we read from tables. At this point, I can able to show you how to read the tables. If you know that, you can skip that part, fast forward. So we are dealing with water, and at 100 kilopascal, let's go to pressure tables. This is saturated water tables. At 100 kilopascal, right, the saturation temperature is 99. Well, it looks like we have a temperature of 30 degrees Celsius, so it is a compressed liquid. It is below the saturation point, so therefore you need to stay in the same table and read specific volume for VF and from here at that temperature we need to go to the other table, right? Temperature table. Now we need to locate our temperature, which is 30 degrees Celsius. So we need to read that as the specific volume of the saturated liquid, and UF if you need it, HF is here, and then SF. So these are our properties. Okay, some slight differences might arise due to some tables are being slightly different, but the values should be very close. Okay, so these are the properties we have read from the tables for our compressed water at the inlet. Now, in order to find that isentropic power, right, so we can say isentropic power per unit mass, I need to multiply it with that, which is the mass flow rate is given to us as 1.35 and times, I'm going to continue here, the specific volume times the pressure difference. It is 4000 minus 100 kilopascal, and this should give us the isentropic power to be 5.288 kilowatts. Okay, so we found it, but it's not enough. We need to continue because we are asked for the actual power, right? So, but we are given, if you go back, the isentropic efficiency, we have figured out what the isentropic power is from the equations we have derived in the classroom for an isentropic steady flow device, and therefore the actual power will be, actual power input to the pump will be let me see, 7.554. So if it was a reversible device, isentropic device, reversible and adiabatic, then the power we need to put in should be just 5.288, but due to it's not being reversible, it has irreversibilities like friction, we need to put a power input of 7.554. Therefore, the efficiency is, the isentropic efficiency here in this case is 0.7. Okay. Now, in the next part, we are being asked to calculate the Exergy destruction. Okay. Exergy destruction, and the way to calculate the Exergy destruction is if the actual power input that is known, if we can subtract the reversible power input, we would be able to calculate the Exergy, the rate of Exergy destroyed. How can we figure out the reversible power? So we can do that from the Exergy balance. And Exergy balance tells us the rate of Exergy getting in minus the rate of Exergy getting out minus the rate of Exergy destroyed is equal to 0 for a steady flow device. And if we know that if we set this to Exergy destroyed to 0, this Exergy input becomes automatically the reversible input, okay, or the minimum input that is required in this pump, and minimum power input. So this will be equal to, of course, let's also write down the what else Exergy getting in with. It is getting in with the mass, right? And it is getting out with the mass. Therefore, if you want to find the reversible power, you should use this equation. Okay, so in order for us to therefore find the reversible power using this equation, and we can also write a more explicit form for this because we know the formula for the Exergy difference for an open system is H2 minus H1 minus T naught. Let's delete that a little bit. Is 2 minus S1. So mass flow rate is given, T naught is known. However, we don't know the second state entropy or enthalpy, and so the question is there a figure out that? So there is. Actually, if you write the energy balance for the actual device, you will be able to figure out the enthalpy at the exit. So let's do that. Let's write down the energy balance for the actual device for this steady flow open system. There's actual power and then energy getting in with the mass, getting out with the mass. You can make it more prettier. Okay, so we have already found the actual power. And the actual power was 7.554. And mass flow rate is given to us. This was kilowatts. and we know inlet enthalpy. Therefore, you can figure out H2. Now at the second state, we figured out enthalpy, but we also given the pressure, right? It was 4 megapascal. Well, you know its pressure is 4 megapascal, its enthalpy is 131.42. You can go to the tables to figure out the entropy. So 4 megapascal means 4,000 kilopascal. At 4,000 kilopascal, our enthalpy is 131.42. Let's look at which is lower than HF. So you still have compressed liquid. Therefore, you can go to saturation tables, right? And figure out what the, or maybe compressed tables. Let's see. We have an enthalpy of 131.42. So it is in between here, right? 131.42. So we can do linear interpolation to figure out what the entropy is. So it should be in between those numbers. In fact, it is 0.4423. So you have to do linear interpolation here to figure out what your entropy is, okay? So, and the answer is for that is 0.4423. All right, after we do this, now next we can do is let's say plug in that information to here, okay? And going back, we plug in the information. Let's skip the units and write only the numbers so we don't crowd the page. And therefore the reversible power input is 5.362. So if there are no irreversibilities, it's a perfect device, then we should have a power input of 5.362. That is the reversible, but the actual input is different, and the difference comes from the destroyed exergy. So that's what we were trying to figure out, and therefore the rate of exergy destroyed, we can find it from actual minus the reversible. And always remember that exergy destroyed is the same as the irreversibility. So the problem might say calculate irreversibility rate or the rate of exergy destroyed. So that is the same thing. All right. And then we were able to again calculate that was what we found here. that is the rate of exergy destroyed. And we can also realize a certain thing here, okay? So isentropic power output and isentropic power input and reversible power input seems like those have two different values, okay? Because isentropic efficiency is also considered an adiabatic conditions, adiabatic together with reversible, so there might be slight difference as such. So the way to calculate destroyed exergy or the rate of exergy destroyed, you need to figure out the reversible power input. And to be able to do that, you will have to use the exergy balance as we have done. And from there, you can calculate the rate of exergy destroyed. And the second law efficiency will be basically the reversible over the actual %71%.